To. Děkujeme Arině a přesuneme se do Japonska za Teklou, která miluje matematiku, fyziku a chemii. A právě tahle vášení dovedla až ke studiu strojního inženýrství v Japonsku. I když řeší složité technické problémy, má dar přiblížit ho jakéhokoliv téma tak, aby dávalo smysl i lajkovi a u ní se i ty nejsložitější vzorce mění v ty srozumitelný a praktický příběhy ze života. Tekla nám teď přiblíží CAD design, moderní dovednost, která spojuje techniku, umění a budoucnost.
Okay, so thank you to Arina again, and now we will move to Japan to Tekla. So Tekla loves math, physics, and chemistry, and this passion has led her to study mechanical engineering in Japan. So even when she is solving difficult technical problems, she has the gift of making the student closer to the topic in a way that it can make sense to them. So with her, even the most complicated equations can become clear and practical stories from life. So now Tekla will introduce us to CAD design, which are our modern abilities which connect technology, art, and also the future.
Thank you so much for the warm introduction, both Lucy and Simona. So now I will first share my screen. I'm gonna say a little bit about myself and how I like to teach the students. So first of all, my name is Tekla. So I'm from Georgia, Tbilisi. Currently, I'm studying in Kyoto, Japan, and my major is mechanical engineering and electrical systems. And my university is Kyoto University of Advanced Science. So my languages of instruction is English and Georgian because, yes, and my IB subject is math, physics, and chemistry. So this is the picture of me and the robots that we built for a competition, the national competition in Japan. So we were very proud of it. It was the first time my university ever participated in this nationwide competition. So we were very excited. So anyway, so why I teach and what is my approach? So first of all, I experienced this in high school myself, is sometimes topics, when you look at them on the surface level, they look so uninteresting and useless. And I always found myself trying to make metaphors or give it like some other meaning than like connected to the something that I really understood and was, to the fundamental points. And I think when I'm teaching, I like to sometimes we have a theory and I like to wander off to the real life situation and real life prototypes of some problems. And for physics and math, it's like everyday life. So to connect it to those topics. And first, when you really understand it and have experienced it on your own, you can really have fundamental understanding. And I think it is very important for students to understand why is it important and why you should be focusing on it. And maybe your future is not going to be math or physics or chemistry, but in everyday life, when it rains outside or when you sit in the subway, you want to know, okay, when it stops, for example, in subway, why does it stop? What is the maintenance that they are doing? Like, why is it taking it so long? So this little part of problems. So the methods that I'm using is guided discovery. So especially with real life situations, I like to, ask questions and lead the student towards the theoretical answer that can be derived from the real life situation. And like analogy anchor, this is one of the things that I did in high school for myself, and I like to also involve students in is, for example, very, very complex topics, for example, electromagnetic theory. Like it is very nice. Sometimes I bring up the Japanese trains because some here they are like on magnetic. So I like to involve the type of analogies. And Socratic dialogue is especially when I'm teaching English and in physics, it is very important to remain open-minded and not close the loops with just theory and just like, oh, this is equation. We should see it as the, big picture of a nature. So the demonstration part. So in the engineering, we do, as you can see, this is a robot, one of the robots, which is Boston Dynamics, Boston University built. So the thing is with CAD, I think for many people it is viewed as not accessible, as oh, it's like only thing that very, very professional, very, very like engineering focused people do. But as you can see, you can even make Lego models, trains, and you can just 3D print it. Like many of my friends here, even business students, they have just 3D printers and they just use it. They just with the software. And I didn't know anything about the software when I came to this university, but then I asked around, like, especially like for engineering and technical subjects, it is very hard, a little bit hard for girls to, uh, get across. Arena would also maybe, agree with me. It's the especially in Asian countries, the concentration of girls is very, very little, so we have to try a bit more. So like I started with a little bit of toys, making them like myself on Fusion. So the big part is that for all students, if it's high school, middle school, and even elementary, it is free to use this because this company, they're like, oh, for children it is the best to be like this, and it is, you can just download it, access, just plug in your school, and it is going to be free. I'm gonna do a demonstration of how to make a fidget spinner because that was a big part of my childhood, my adolescence. So I'm gonna demonstrate it a little bit here. I'm gonna share the screen. Okay. So this is how the working space looks like. Okay, at first it's like so many buttons. It's gonna be so confusing at first. No, it's fine. So first we need to create a sketch, of course. So for sketch, we view everything in a three dimensions. We have side, top or bottom, and left or right. So because it's fidget spinner, we are gonna choose the top one. And for fidget spinner, it is important the circles, of course. We put circles, one circle. It's a 3-circle fidget spinner. So as you can see, the circles are, different diameters. So here where the mathematics comes of the geometry, we are gonna change the diameters to whatever number that we are thinking. For example, 40 millimeters for all of them. Like this. And then the knowledge of triangles comes in. So we are gonna connect the centers of this. Let's make it, let's make this, let's make it 60. So it is the distance between them is 60. So we are gonna assign them like, okay, like this. Okay. So what we are gonna do now is we all know the triangle, like regular triangle, which all the sides are the equal. So we are gonna go here equal, and we are gonna make everything equal to each other. This side is equal, and this side is equal. Okay, so now we have a 60-degree angle triangle. And what we are gonna do now is a fidget spinner, the angles are not very sharp. So what we're gonna do is make arcs. Here where knowledge of arcs comes in. So we are gonna connect them. And for the arc, the radius, we are gonna choose, let's say 14, because why not? So here we are gonna repeat. So a lot of this process is actually repetition and, guessing the numbers sometimes. Sometimes it's very, very precise. But in mechanical, you can, in mechanical engineering, I think it's it allows you more to make a bit of mistakes. I think for aerospace engineering, it is very, 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 very strict. So everything, even a little detail, if it's off, yeah, Arina would know. So, wait, so now we are gonna, okay, wait, okay. So we want to now make them tangent to each other. So here where the knowledge of tangent comes in. So we're going to make everything connected together with a tangent. So in this program, we are using a lot of mathematical concepts, as you can see. So when I first used this, I was like, aha, that's why I learned math. That's why it's important. So we have a general shape of fidget spinner, but as you know, fidget spinner has holes inside it. So we can make a concentric circle. Again, geometry. So we are going to make concentric circle. Let's make it 20, maybe 25. It's more visually pleasing like that. Okay, 25 for each of the circles. Yes. So I'm not gonna go into a lot of details of yeah, I think it looks pretty nice. So when we are finished with the sketching, general shape, we have it there. It looks okay enough. So what we are gonna do is extrude. So in high school and especially in IB, you are guys gonna learn integrals. And for the longest time, you're gonna think, where is integrals used? Why would you use it? So when first time I learned about this command extrude, what it does, it takes the function, the graph that is drawn, we will select each of the areas. And what it does, what it does is it integrates it to the space. We are gonna push it up. Let's make it maybe 10, maybe fidget spinner type. So see, we have now a fidget spinner, which is a bit minimalistic, but still there. So see, integrals also very important here. And if you want, then we can change the material. Like here we have we can make it glass, liquid metal, anyway, whichever. For example, if we change it, aluminum is already what I have. For example, brass, it will make a yellowish color, bronze, so on. It's really like our choosing. And if we want to make it a bit softer on the sides, we can soften it a little bit up and down. So it's like very fun to get started with. And here we have a 3D printer spinner, and here it is. Okay, thank you so much. I hope it was not too difficult and not too too much. Thank you so much, and yes, that's all.
Thank you so much. At least for me, it was very interesting to see this because I've never seen it used before. And I wanted to ask, why did you use specifically CAD design and why not something else? Like for this demonstration?
Yes, because overall, like I'm a second year student, so during these 2 years, I have worked I worked a lot to develop the CAD designing skills to that level, and doing even in my free time, I find myself doing CAD because it's so enjoyable to me. When you actually put on music and just you get in the zone, it is very, very enjoyable. So I thought about this demonstrating something that is like very enjoyable to me, because when I speak about it, I think it is nice to listen to. So yes.
Yeah, definitely. And since you worked with it so much, what is maybe in your opinion like the coolest thing that you have designed on there?
It was V12 engine. It was the first engine that was put in the cars, for example, in the Ford, if you guys know the old ones. I don't think I have a file open right now, but it was like very, very, it was one of the most complex things that I did myself without any help, and I was very proud of myself. I was like, oh, I've achieved the level. Yes.
Yeah, it sounds really, really cool. And I have one more question before, not about CAD design, but in the beginning you talked about how you use like analogies to real world. So maybe can you think of like an example of a like time with a student where you used such an analogy and it helped the student to understand like a difficult topic?
Oh, yes. So I was explaining for chemistry, we have the periodic table. And one of my students, she does a lot of sports. So I didn't want to get into the orbitals and so on, like right on top. So she asked me like, oh, why are they arranged like this? So they have numbers, like atomic numbers on top. So I told her, like, think of the atomic numbers as, for example, like during marathon, you have a number on your back. So each of the chemical elements are marathon participants. So for example, like first one, hydrogen is running as a number 1. So each of them are numbers. So that's how you can tell that's a atomic number. So they are each numbered like that. So she was like, oh, okay, okay. And more about like when we were talking about energy, I explained to her like this, we have kinematic energy and we have potential energy. So she does a lot of running. So I was like, well, what if you run up the hill? You have a velocity, which is starting at the beginning, and at the end, you're going to be a bit slower because you're running up. So you have kinetic energy, but because you're running up the mountain, your height is changing also. So you're gonna have potential also. But if you're running on the plane, just going, just speed, no height change, then it's just kinetic energy. So I like to relate stuff to what student is curious about. So when they actually think of topic like, oh, like when I run, if the ball is gonna go, if car is going from the bottom to the up, it's gonna be the same analogy that is directed towards the student. Yes. Thank you.
Thank you. It's really interesting. I even felt like I learned something from this explanation, so thank you. And yeah, that's all for the questions. Thank you
Thank
again.
you so much.